Calculus, video 51, optimization. So in optimization, we are determining the maximum or minimum that something can be given certain constraints or certain parameters. So we're looking to try to find the maximum or minimum, one or the other. The problem will tell us which one we're looking for in a certain situation. Let's go ahead and start by looking at just some general rules or goals about how to determine an optimization problem, how to find this maximum or minimum. So step one is we want to find or create an equation that describes the event that's happening. All right, so what are we doing? That event, we want to get an equation that describes that event under the constraints that are given in the problem. So for example, maybe we're looking to maximize the area of something. That's the event. We want an equation that allows us to maximize the area. So an area equation. Or maybe we want to minimize the distance between two things. So we would need a distance equation. Or maybe we want to minimize the cost of something. So we would need a cost equation. So we are either going to find or create an equation that describes the event, and we'll have certain constraints under which we will do those things. Number two, we're going to determine either the absolute max or the absolute minimum of the equation. Again, which one of those will be determined in the problem. The problem itself will say minimize the cost or maximize the area. So we're finding one, but not both. If you remember, to find the absolute max or absolute min, we look in two places. One is we need to look at the endpoints. All right, so we'll take a look at the endpoints. And two, we will look at the relative extrema. Your absolute extrema, your absolute max or min, will come from either the endpoints or the relative extrema. And for the relative extrema, we should recall that will occur either when the derivative is equal to 0 or the derivative is undefined. So once again, we are looking kind of like when we did curve sketching. We're looking for when the derivative is equal to 0 or undefined, and we're also, because we're looking for absolute max or min, checking the endpoints. So we get the equation under the constraints. We take the derivative, we find out when is the derivative equal to 0, when is the derivative undefined, those are our critical points. We take our critical points, we take our endpoints, and we find out which one is the absolute max or perhaps which one is the absolute minimum. That's the general idea. However, step 3 here, and actually shouldn't really call them steps because step 3 often comes before step 2. Once we have the equation, there are times when our equation is in terms of multiple variables. We've seen that maybe over in related rates, where we might have a volume equation, say for a cone is 1/3 pi r squared h. And we didn't take the derivative of both sides until we made the right-hand side only in terms of one variable, right? So we would relate r and h somehow and then substitute, say, r in for whatever h is. R is equal to 5h, something like that, and substitute it in. That way I get the right-hand side only in terms of one variable. The same thing's going to happen here because I'm going to have an equation that I want to take the derivative of both sides, but sometimes on the right-hand side you get two variables, like an r squared and an h. And we need to find a secondary equation that relates the two variables, something that relates, say, r and h, for example. Solve for one of those variables in terms of the other and substitute it back in so that you only have one variable on the right-hand side. Okay, so that often happens before step 2, before we take the derivatives. We only have one variable on each side. And again, not step 4, but just kind of number 4 thing to think about. Drawing pictures is often helpful, even possibly necessary to draw the picture so that we can figure these things out. So highly recommend that you're drawing pictures when we're doing optimization problems. Okay, let's try one. I have our first problem, example 1. Go ahead and pause the video, write example 1 down. it says that you have 200 feet of fencing and you want to build 2 equal-sized pens of maximum area. So pens here, like pens for keeping animals, kind of a thing. So you want to build 2 equal-sized pens, so they need to be the same size. You want the pens to have maximum area. On one side is a river, so no fencing is needed on this side. What should be the dimensions of each pen? Okay, let's see if we can work that. So again, we're thinking we need an equation that describes the event that's happening. And the event that's happening is we are trying to maximize the area of these pens. That's the event. We're creating 2 pens. We want to maximize the area of those pens. There's a river on one side, so we don't need fencing on that side, and we have a total of 200 feet of fencing. Again, a picture is probably going to be quite necessary here. So let me draw the river. Here is the river on which there is no fencing needed on that side. I would like to create 2 pens. So 2 pens means that I'm going to have a pen that looks maybe like this. There's one pen and another one the exact same size. I think the best way to create that would be to put them something like this. All right, so 2 pens up against the river, maximizing the area of those pens, noting that I have 200 feet of fencing. And we want to maximize area. And the question is, what are the dimensions of each pen that would maximize the area of the pens? All right, I think labeling these things, creating variables for them is probably the best step next. So I should have said this. I did not in my problem. These should be rectangular pens. I'm going to add that into my problem because, I mean, we could have made circular pens or semicircles or something like that. I needed to say in here rectangular. That's my fault. Okay, we would like to build 2 equal-sized rectangular pens of maximum area. So I have drawn rectangular pens. Again, let's go ahead and put some variables where they need to be. How about an X here? And since this is a rectangle, if this side is X, that means this side is also X here and also X here. And so that's like the width of each pen. No fencing is needed along the river, but we do need some sort of a fencing on the back end here. So let's call this Y here. And because these 2 pens must be the same size, let's call this Y here. Okay, we want to maximize the area of each pen. So what would the area of each pen be? The area of one pen area is equal to X times Y. That would be the area of, say, one of the pens here. It would just be X times Y. So I want to maximize that. I want to take its derivative. I want to find out when this is equal to 0. I want to find out when it's undefined. And I want to check the endpoints. And then find out which is the absolute maximum. Again, we have A is equal to X times Y. I have 2 variables over here, X times Y. So what I want to do is make that just one variable. And the constraint that we have is we only have 200 feet of fencing. All right, so the fencing that we're creating is 200 feet. We'd like to use all 200 feet if possible. And so our secondary equation that we can relate X and Y to is that the total fencing used is 200. And to create my pens, I have 3 X's and I have 2 Y's. And that amount of fencing is equal to 200. Okay. This is going to allow me to relate X and Y. I'm going to then solve for one of the variables, substitute it into my area equation, and then be able to take the derivative. Okay, let's see, let's solve for y. It seems dividing by 2 seems easier than dividing by 3. That's the only reason I'm solving for y here. Solving for y, 2y is equal to 200 minus 3x. Divide by 2, y equals 100 minus 3 over 2, or 1.5x. Take your pick. Okay. I'm going to take that y value, I'm going to substitute it into my area equation. So now area is equal to x times 100 minus 1.5x. Or if we distribute, area is equal to 100x minus 1.5x squared. Okay, this is good. We now have our area equation in terms of one variable. Area equation in terms of one variable. Once we have that, we can then take the derivative. We can find out when the derivative is equal to 0, when the derivative is undefined, that's our relative extrema, and then we can check the endpoints. So let's do the derivative, and then we'll go back to the endpoints at the end. So a prime is equal to derivative with respect to x is 100 minus 3x. So the question is, when is a prime equal to 0? And when is a prime undefined? A prime is equal to 0 when 100 minus 3x is equal to 0. A prime is undefined, well, never. That's just a linear polynomial. So solving this one up here, I get 100 equals 3x. X equals 100 over 3. Okay, so my x value is 100 over 3. Let's find the corresponding y value to that. We know that y is equal to 100 minus 1.5x. So if x is 100 over 3, then y equals 100 minus 1.5 times 100 over 3. Or maybe the fraction works out better here. That's 100 minus 3 over 2 times 100 over 3. 3's cancel. 100 minus 100 over 2, that's 100 minus 50. That is 50. So here's what my dimensions are for my relative extrema. I get an x, y value of 100 over 3, or 33.33 repeating, for my x value, and a y value of 50. And those are in feet. I should probably go ahead and use the dimensions there, 100 over 3 feet and 50 feet. Okay, so those are my relative extrema. And what we want to see is that the maximum area? But before we get there, let's talk about endpoints. Honestly, most of the time, the endpoints aren't the answer here. The endpoints end up being kind of the extreme of possibility. So for example, the endpoint here, if we're going back up to our picture, the endpoint we like, well, what's the smallest that x could be? What's the smallest that y could be? What's the largest that x could be? Well, the smallest that x could be would be 0. In other words, like the x, in order to make a fence, that the smallest the x value here could be 0, it really has to be more than 0 to make this work, to actually have a pen. But if x were 0 and each y was 100, you would have used all 200 feet of fencing, but your area would have been 0 because there'd be no actual area there. So that would be one endpoint, is when x is 0, but you get no area. You get a minimum area of 0. The other endpoint there would be if all of the fencing went into your x's and you had no y's, right, where the y value is 0. And so your 200 feet of fencing would be divided by the 3 x's, so 200 divided by 3 for each of the x's. All the fencing used to make those lines, and your y is 0, you'd basically have 3 fences just sitting right next to each other. Again, no actual area. So the the endpoints here say for x. X is going to be between 0 and, at maximum, 200/3. If all of the fencing is used for the x values, none of the fencing used for the y values, I have 3 x's, so 200/3. That's my endpoints. But in each of these cases, the area would be 0, because I really wouldn't even have a pin. There'd be no actual area. There'd be just 3 fences lined up next to each other. Or if x is 0, I've got a fence line, each y being 100 foot, but it's right up against the river, right? There's no actual area there. So in this case, the endpoints are giving us minimums, not maximums. The maximum area is going to come from when x is 100/3 feet and when y is 50 feet. So endpoints here give area equal to 0. They minimize the area. The maximum area has dimensions 100/3 feet by 50 feet. I don't think I asked for it, but we could find that maximum area. I think I just asked you for the dimensions of each pin. Okay, that would be the dimensions of each pin. If you multiply those two together, the area of each pin, didn't ask, but might as well find it. Area of each pin. Then we could take the area, which we know is x times y. Area is equal to 100/3 times 50, 5,000/3, or approximately equal to 1666.67. Probably should have known that. Approximately 1667 square feet.